In 11.1 and 11.2, we are going to learn about permutations and combinations. What this means is that we are counting the number of ways that we can collect and organize items. Both permutations and combinations are applications of the fundamental counting principle. So that is where we are going to begin. We're going to start by looking at this example here. Imagine that you are getting dressed in the morning and you have the following options: 4 pairs of snazzy jeans, 3 very hip t-shirts, and 2 pairs of cool shoes. How many different outfits can you create using these items? So you'll notice that this question starts with how many, and most of the questions in 11.1 and 11.2 are going to ask this: how many? So we are counting the number of ways that we can complete the task. For this example, we're going to start by creating what's called a tree diagram to demonstrate the sample space. The sample space is just all the possible outcomes. Once we have written what all the possible outcomes are, we can count how many we have and answer the question. In our tree diagram, we start with the jeans. So we've got 4 pairs of jeans, which we can see are all listed there. Branching off each pair of jeans, you'll notice that we have 3 choices representing our 3 t-shirts. So if I choose jeans 1, I have 3 choices: t-shirt 1, 2, and 3. If I choose jeans 2, I have 3 choices: t-shirt 1, 2, and 3. Same with our 3rd pair of jeans, and same with jeans 4. Then you'll notice that off of each t-shirt, we have branching off 2 items, which represents our 2 pairs of shoes. So if I choose jeans 1 and then t-shirt 1, now I can choose between shoes 1 and shoes 2. Same thing here. If I choose jeans 1 and t-shirt 2, I've got 2 choices: shoes 1 and shoes 2. What we're going to do now is count how many branches we have at the bottom of our tree. And if we count here, there are 24 items. What that means is that is the answer to our question. So our answer here would be 24 different outfits that can be created using 4 pairs of jeans, 3 t-shirts, and 2 pairs of shoes. Now, this method of solving by drawing the tree diagram and then counting up the number of branches at the bottom of the tree is great. It answers the question. However, it is quite inefficient. Also, the tree diagram actually lists out what all the possible outfits are, but that's not what the question is asking. The question isn't asking what are the outfits, it's just asking how many there are. So what we need is another way that's going to calculate the number of different outfits without having to write out all the different outfits. And that method is going to be the fundamental counting principle. So let's read this paragraph here. If a task is made up of several stages or several choices, and there are m ways to accomplish stage 1, n ways to accomplish stage 2, and p ways to accomplish stage 3, and so on, the total number of ways to accomplish the overall task is m times n times p. In other words, you're going to take the number of options at each choice and multiply them by each other. That is your fundamental counting principle. So if we took that and used it in the above example, we start with having 4 options for jeans. So I'm going to write 4. We have 3 options for t-shirt. So I'm going to multiply by 3. And we have 2 pairs of shoes. We're going to multiply by 2. 4 times 3 times 2 gives us 24, which is how many we counted on our tree diagram. So that's a much shorter, easier way of calculating the number of outfits without having to draw out the whole thing. We can use that in other examples that are also using the fundamental counting principle. They're going to be a bit different than the outfit question that we asked, but we're going to set it up in a similar way. Let's look at example 1. If your bike lock consists of 3 digits, how many different lock combinations are there if any digit from 0 to 9 can be used? So in this case, we also have 3 stages or 3 choices because we have the 3 digits there. So I'm going to start, whenever I have a certain number of stages, I'm going to start by writing down blanks that represent the stage. So I'm going to draw 3 blanks here. that represents each of the 3 digits. And then on each blank, I'm going to put a number which represents the number of choices at that stage. So for digit number 1, I can use any of the digits from 0 to 9. That means I have 10 options to choose from, so I'm going to write 10 in that blank. Same thing with the second digit. We can use any of the digits from 0 to 9. It doesn't say anything about we can't use a number more than once, so I'm going to assume I can use them as often as I want. So I'm going to have 10 options there as well. And then in the third grouping, we also, or for the third digit, we also will have 10 options there as well. Fundamental counting principle says to take the number of options at each stage and multiply. So we're going to multiply 10 times 10 times 10, and that is going to give us 1,000. So there are 1,000 different lock combinations if we have 3 digits, and any digit from 0 to 9 can be used. Example 2 builds off that same example. What if, in the above example, no digit could be replaced? So we still have our 3 blanks, or our 3 choices, our 3 digits. So I'm going to start by drawing the 3 blanks, which represents our 3 stages, our 3 digits. In that first blank, I'm going to think about how many choices I have. I can use any digit from 0 to 9, so that is 10 choices. However, in the second blank, I cannot use the number that I put in the first blank. So that means I have 1 less digits to choose from, so 9 choices for that one. I've now used 2 of the numbers that I cannot use again, which means now I only have 8 choices for the third blank. Fundamental counting principle says to multiply those numbers together, and we end up getting 720 different lock combinations. You'll notice that we get less possibilities in example 2 and example 1, because in example 2 we have what's called a restriction. And anytime you put a restriction or a rule or a constraint, you're going to get less possibilities. Some problems will contain restrictions and constraints. So if we can, we're going to deal with them first. In example 3, we are creating a 5-digit number. And so just a quick note about these kinds of questions. It's different than creating a PIN code or a lock code in that we have to really be careful about our first digit. So I'm just going to make a note down here and talk for a minute about creating numbers. For example, in this one, we want to create a 5-digit number. So something like 50,921 is a 5-digit number. Something like this, if I put a 0 first, and then let's say we go 1, 7, 6, 5, that technically is not a 5-digit number. That's just 1,765, which is not a 5-digit number. So when we are creating numbers, there is automatically going to be a restriction, and that restriction is going to be that the first digit cannot be 0. Now, in this question, we've actually limited the first digit already, but in other questions that you might have, just keep this in mind that we will always have that restriction when we are creating numbers. So in example 3, we are creating a 5-digit number. So I'm going to start with writing my 5 blanks, or represent our 5 stages. And in this case, we have a couple of restrictions. First of all, it has to be an even number. Now, when we decide if a number is even or odd, we always look at the last digit. So I know that I have a restriction on this last digit. It has to be even. That means that it has to end in a 0, a 2, a 4, a 6, or an 8. So we've got 5 choices for that last blank because we must create an even number. So that was a restriction, and we're going to start with that. Keep on reading, and it says that this 5-digit number has to have a value greater than or equal to 70,000 but less than 90,000. Now what that is showing is a restriction on the first blank. It has to be greater than or equal to 70,000, which means we can start our number with a 7. We could also start our number with an 8, but we cannot start our number with a 9 since it has to be less than 90,000. So that means our restriction on the first blank is that we can only have 2 digits to choose from there. Now that we've taken care of our restrictions, we can look at those blanks that do not have a restriction. These 3 blanks, we can use any number from 0 to 9. So 10 choices for this blank, 10 choices for the middle blank, and 10 choices for that one. Fundamental counting principle says to multiply our number of choices together, and our answer would be 10,000 different even numbers with a value greater than or equal to 70,000, but less than or equal to 90,000. So those are 3 examples where we are using the fundamental counting principle to calculate the number of ways to accomplish a task. We had an outfit question, which sometimes also appears as a menu question where you've got certain items to eat at certain stages. We have a bike lock question, which is also similar to a PIN code question. And then we had example 3, which is creating a number. So let's go ahead and move on and let's talk about permutations. So a permutation is, or when we're calculating permutations, what we are doing is applying the fundamental counting principle. These questions are slightly different. First of all, we are starting with a finite number of objects, and what we are doing is we are arranging those objects. So the word arrangement is going to be key here. And what also is important is the order of the items is important. So what that means is if I take multiple items but change the order of the items, that creates a new arrangement or a new permutation. The other thing that's important about permutations is that none of the objects can be repeated or reused. So we have a finite number of objects that we are arranging, and once we've used that object or placed it, it cannot be used again. So let's start with a simple example, and that is arranging the letters T, O, and M. So you need to sort of picture in your head that we have 3 blocks. One has a T on it, one has an O, and one has an M. Because we have 3 letters, we can start with T, O, and M, the original arrangement. We may want to keep the T in its original spot, but switch the order of the M and the O. That creates a new arrangement or a new permutation. From that one, we might switch the order of the M and the T. So we have M, T, O. There's a 3rd permutation. We could then switch the order of the O and the T. So M, O, and T. Maybe we want to put the O in front and then the M and then the T. And if we switch the order of the M and the T again, we have O, T, M. Now we can continue to interchange the letters, but that's not going to provide us with any new permutations. So if we look at what we have here, we have 6 different permutations or 6 different arrangements of those 3 letters. Now, similar to the tree diagram, this listing of the possibilities does solve the question, but again, like the tree diagram, it's inefficient, and we don't actually need to know what all the arrangements are. We just need to know how many there are. So that's what this paragraph here speaks to. While the method of writing the possible permutations works here, it would be increasingly difficult when more items are arranged. The more items that we have, the more arrangements there are. Instead, we are going to use the fundamental counting principle. We have 3 letters, so we have our 3 stages. We are starting with holding on to those 3 letters, which means I have 3 choices for that first position. Once I've put down one of the letters, I cannot use it again, which means we have 2 choices for the second position. Once I put that letter down, now I only have 1 left. That's how many choices for the third position. Fundamental counting principle says multiply 3 times 2 times 1 is 6. Let's do the same with example 4. How many permutations, so there's that word permutations, which tells us that we are making arrangements, of the letters of Kelowna are there? So what I like to start by doing is counting up the number of items we have here. So there are 7 letters that we are arranging, or 7 items. The other thing that we want to check for is we want to make sure that each of those items is distinct, that we don't have any repeating or identical letters. And in this case, we don't. So we have 7 distinct items. All of the letters are different than the other letters in the word. So because we have those 7 distinct items, I'm going to draw 7 blanks. And I'm going to start to arrange the letters. For that first blank, I'm holding on to all of the letters. That means I have 7 choices for that first position. Once I've placed a letter in the first position, I cannot use it again, which means I only have 6 choices for the second position. Because I cannot use either of those 2 letters again, we've got 5 choices for the next. 4, 3, 2, and then finally 1 choice for that last spot since we've put down the rest of the blocks. Fundamental counting principle says multiply those together. 7 times 6 times 5 times 4 times 3 times 2 times 1 is 5,040. So there are 5,040 ways to arrange the letters of the word Kelowna. Example 5. How many ways can 5 people be lined up for a photograph? So that means we are arranging people in a line for a photograph, which means we're talking about a permutation. We have 5 items here, and because we're talking about people, people are always distinct items. So I'm going to start by drawing my 5 blanks to represent the 5 positions I have for the photograph. I have 5 people, so I have 5 choices for that first position. Once I've placed somebody in their position for the photograph, I cannot change them or move them again. That means I only have 4 people choices for the second position, then 3, then 2, then 1. Fundamental counting principle tells us to multiply the numbers together. We get 5 times 4 times 3 times 2 times 1, which is 120. We should be noticing a pattern here. When we were arranging the 3 letters, our fundamental counting principles gave us 3 times 2 times 1. When we were arranging our 7 letters, 7 times 6 times 5 times 4 times 3 times 2 times 1. And when we are arranging the 5 people, 5 times 4 times 3 times 2 times 1. So it looks as though anytime we are arranging n objects, where we're using all n of them, ends up being n times n minus 1 times n minus 2, and so on. Well, instead of pushing all the buttons in our calculator, we actually have a bit of a shortcut for multiplying these kinds of numbers. A shortcut to multiplying consecutive natural numbers in decreasing order to the number 1 is called factorial notation. And what it looks like is an exclamation point, which looks a little different, but we would write n factorial, which is n. So we always start with the number that we have in front of the exclamation point, n times 1 less than n times 1 less than 2 less than n, and so on. And we keep going down by 1 until we get to 3 times 2 times 1, which means if we back up here to the letters of T, O, and M, 3 times 2 times 1 is 6, but we could have also written that as 3 factorial. Same thing with example 4, 7 times 6 times 4 times 5 times 4 times 3 times 2 times 1. We could have written that as 7 factorial. And finally, in example 5, 5 times 4 times 3 times 2 times 1, is 5 factorial. We also have that functionality on our calculator. So what we do is we start by putting the n value. For the first one, it is 3. We go to our math menu. We arrow across the top and go into our probability menu. It looks like this, PRB, or in some older calculators, just PR. This one's PROB. Sometimes it's just PRB. And you can see that number 4 has that exclamation point that represents the factorial. So there's 3 factorial, which is 6. In the second one, we had 7 times 6 times 5 times 4 times 3 times 2 times 1. We can shortcut that. 7, math, across to your probability menu. Then number 4, there's 7 factorial. The last one was 5 factorial, so I put in 5, math, go to the probability menu, number 4, enter. So we don't have to push all of the buttons. We can actually just put the factorial notation into our calculator. In the next example, we are going to use factorial notation to simplify and evaluate some expressions that contain factorials. So if we look at example 6, we do have 2 steps. We want to simplify the following, then evaluate. Now, you might say, looking at A and B, couldn't I just take those values and put them into my calculator and get an answer? And yes, you could do that. What we want to do is we want to see how to simplify A and B, because if we sneak a peek at part C, that we cannot put into our calculators. So we do need to look at how to simplify in factorial form so that when it comes to questions like C that we can't put into our calculator, we are able to do that simplifying. So we're going to start with A, which is 10 factorial divided by 7 factorial. What we want to do is we want to choose the n that is bigger. So because 10 is bigger than 7, I'm going to take that numerator, 10 factorial, and I am going to expand it using what factorial notation means. Okay. Definition of factorial notation is that n times n minus 1 times n minus 2 and so on. So starting at 10 for 10 factorial, I'm going to write this as 10 times 9 times 8 times 7, and I'm going to stop the expansion at 7. After 7 comes 6, 5, 4, 3, 2, 1. So the rest of the expansion, I'm going to write as 7 factorial because the rest of the expansion is 7 factorial. It's 7 times 6 times 5 times 4 times 3 times 2 times 1. The reason I'm stopping at 7 factorial is because that is what is in the denominator. What that means now is I can cross out the 7 factorial and all its terms with the 7 factorial and all its terms in the denominator. They end up dividing away. And all we're left with is 10 times 9 times 8, which is 720. So again, we choose the n value that is higher. We expand that factorial using the definition of a factorial, but we only expand until a point where we can simplify, and then we evaluate. In part B, I see a 37 factorial, a 34 factorial, and a 3 factorial. 37 is the largest number, so that is the one that I'm going to expand. We start with 37. We do 1, go down again, 35, one more, 34, and I'm going to write the rest of the expansion as 34 factorial. I'm stopping at 34 factorial because 34 factorial is one of the terms that we have in the denominator. So the 34 factorial in the numerator takes out the 34 factorial in the denominator. Now, the 3 factorial that we have in the denominator, we should recognize 3 factorial as 6. So what ends up happening there is that factor of 6 in the denominator can reduce the 36 in the numerator, leaving us with a factor of 6 in the numerator. And then all we have left to do is to multiply 37 times 6 times 35. So we can put that into our calculator to get a value for that. So 37, times 6 times 35. And then our answer is 7,770. So we can put that as our evaluation. So again, we take the bigger n value, expand it using the definition of factorial, and then reduce from there. Same thing in part C. So in part C, we won't have the evaluation part at the end, but we definitely can do the simplifying part. I have an n minus 3 in the numerator and an n minus 1 in the denominator. N minus 1 is going to be greater than n minus 3. So that is the one that I'm going to expand. So for now, the n minus 3 factorial in the numerator is just going to stay. But n minus 1, let's expand. We start with what we see, so we start with n minus 1. We reduce it by 1, so n minus 2. Reduce by 1 again, n minus 3, and we will write the rest of the expansion as n minus 3 factorial. We stop at the n minus 3 because that is the factor that we have in the numerator. So the n minus 3 in the denominator has taken out the n minus 3 in the numerator. That leaves us with a 1 in the numerator and n minus 1 times n minus 2 in the denominator. I'm just going to expand the denominator. That's going to give us n squared minus 2n minus n, collecting like terms, minus 3n plus 2. That would be our final answer for C. That's the simplification we can't evaluate. Now, we can see that the factorial notation is linked to permutations. And then now we've talked about simplifying using the factorial notation. So what we're going to do is take those two things and put them together. And what we're going to talk about is we're going to talk about those instances where we have n objects, we're holding on to our n finite objects, but we do not want to arrange all of them at once. So I just want to take a few of them. I want to take our objects and I want to arrange them. Well, we have a formula that helps us calculate the number of permutations. And what it looks like is this. So we have two parts to it. We have that form NPR or n permute R. And then we have a formula for n permute R, which is n factorial over n minus r factorial. When we have questions where we are not arranging all the items at once, if we have n and r, then we can use our calculator to calculate the number of permutations. But if we are missing n or r and we want to calculate n or r, understanding the number of permutations, we're going to need the formula, and that's where the simplification is going to come into play. So let's look at the next two examples. They are examples where we would use NPR. 10 boys are running a cross-country race. In how many ways can the gold, silver, and bronze medals be awarded? So we have 10 boys, but we only need to arrange them 3 at a time. And this is a definite arrangement because we are dealing with placements here. We have gold, silver, and bronze. So the order in which we list the 3 boys that we choose is going to have an effect because whoever we pick first gets gold and silver and bronze for the second and third. So it is a permutation because order matters, but we have 10 items that we are arranging. So n is 10, but we only have 3 positions. So our r is 3. Our answer then becomes 10 is the number of objects. It's a permutation, so we're going to use the letter P, and we're using our items 3 at a time. We can do this on the calculator. So we would put in the n value first, so put in that 10. Go to your math menu, and again, back to that probability menu, and you can see number 2 says NPR. So we're going to do number 2, and then go ahead and put that R value in there, which is 3. So that gives us 720 ways that the different ways that the 10 boys can be in gold, silver, and bronze. So equals 720. We could use the formula here. It would be 10 factorial divided by 10 minus 3 factorial, which is equal to 10 factorial divided by 7 factorial, which we could then simplify or put into the calculator in that form. It's still going to give you 720. In example 8, if a vehicle license plate in one province consists of 2 different letters followed by 4 different digits, how many license plates are possible? Okay, so first of all, we know that this is a permutation because in a license plate, the order of the letters and numbers matter. If we switch the order of the letters or numbers, it creates a new license plate. So we know that, for example 8, we are talking again about a permutation. Now, we are dealing first of all with 2 different letters. So for that part, we have n equals 26, and that 26 is coming from the number of letters in the alphabet, but we only need to arrange these letters 2 at a time. So R would be equal to 2 for that part of the arrangement. Then it's followed by 4 different digits. So we know that we have 10 digits from which to choose, but we are only going to be arranging them 4 at a time for this problem. Okay, so we're dealing with permutations. We know our N's and R's. So let's go ahead and write down our formula. It's going to be 26 permute 2, and it's going to be 10 permute 4, and we are going to multiply in the middle. Again, that fundamental counting principle comes into play here again. And again, we can go to our calculator to do this. So I'm going to put in the 26. We're going to go to our math menu. We're going to go across to the probability menu, choose number 2, and then we're going to put in our R value of 2. You may have to arrow over, put in your multiplication, and then the 10 for our N value of our next set of digits, across the top to the probability menu, number 2 again, and then we are arranging them 4 at a time, and the calculator does it for us, so we get 3,276,000. 3,276,000. And that's how you can use and permute R to solve chapter 7 or example 7 and example 8. Now I do want to go back and do example 7 and example 8 a second way, just to show you that some of these permutations questions have multiple solutions, multiple strategies for solutions. So we did decide in example 7 that it was a permutation and that we were arranging these boys 3 at a time. We could also do this with more of a fundamental counting principle strategy in mind. We have gold, silver, and bronze. So there are 3 stages or 3 decisions we need to make. When we're deciding who gets gold, we are starting with the 10 boys in total. Once we've given gold to one boy, he cannot be given another award. So we've got 9 choices for silver. And then we would have 8 choices for bronze. 10 times 9 times 8 gives us 720. So whether you recognize this as a permutation question and an NPR question, or whether you recognize it as a fundamental counting principle question, both equally good strategies to use, and you should be aware of both strategies. Similar with example 8. So we recognized it as an NPR question. We could also approach this question as a fundamental counting principle question. So we have 2 blanks for our 2 letters, followed by 4 blanks for our 4 digits. Starting with our letter, we've got 26 options. We can use any letter in the alphabet, but because it says 2 different letters, I cannot use whatever letter I put down, so I only have 25 choices for the second letter. Now we're moving to our digits. For the first digit, we have 10 choices, but it does say 4 different digits, which means whatever I put down in that blank, I cannot use again. So only 9 choices for the next spot, 8 choices, 7 choices for the last position. Fundamental counting principle says multiply all 6 of those together. We're going to get the same thing. Oops, I forgot a 0 over here. Just make sure we should get the same thing. We should get 3,276,000 again. So we get the same answer. We get the same answer whether we approach it using a permutation or approach it using a fundamental counting principle, but you should be aware of how to do both. Now we're going to skip through a couple of examples, and we're going to look at an NPR question where we don't know N and R. So example 13 says, use the formula NPR equals N factorial over N minus R factorial to algebraically solve for N given that equation, N permute 3 equals 60. So we can't just go and put this in our calculator. Because we're missing N, we can't put it into our calculator. We also don't want to just start guessing values of N and choosing NP3 in our calculator over and over again until we get 60. We want to solve this algebraically. So we are going to start with the formula, and we're going to start with the fact that we have N permute 3. So taking the left-hand side and using the formula, N is N, so we start with N factorial over N minus, we know what R is 3, N minus 3 factorial equals 60. So that gives us our equation. In order to solve this equation, we are going to need to simplify. Well, we know how to simplify. If we back up and go back to when we were talking about that factorial notation and the definition of factorial, like part C, we were able to simplify factorial expressions. So that's what we're going to do in this example as well. N is bigger than N minus 3, so that is the part that I'm going to expand. We're going to use the definition of a factorial to do it. We start with N, multiply by 1 less than N, multiply by 1 less than that, 1 less again, and we're at N minus 3. So I'm going to continue the rest of that expansion by just writing it as N minus 3 factorial. We are stopping at N minus 3 factorial because that is what is in the denominator. Don't forget to keep writing it as an equation so that 60 is going to stay on the other side. We can simplify, so the N minus 3 factorial takes out the N minus 3 factorial, and now we have an equation without that factorial notation, which is great. I'm going to expand on that left-hand side. So I'm going to start by multiplying that coefficient into the binomial, which gives us N squared minus N. We still have the N minus 2, and it still equals to 0. We are to 60. We're going to expand these two binomials. So we are going to get N cubed. So N squared times N is N cubed. We're going to have a minus 2N squared minus N squared, collecting like terms, is minus 3N squared plus 2N equals 60. And now we are solving a cubic polynomial algebraically. So this is a nice review of chapter 3. The first thing we do is we set that polynomial equal to 0. So I'm going to subtract 60 from both sides. And now we want to solve the polynomial. We have to factor the polynomial. So what I'm going to do is I'm going to start actually by graphing that polynomial so that I can grab 1 0 that I can use as a factor. So there is the polynomial already there. We hit graph, and I notice that we have a 0 at positive 5. We have a 0 at positive 5. What that tells me then is x minus 5 is a factor. We'll do synthetic division in order to find the other factors. So 1 is my coefficient, then -3, then 2, then -60. Bring down that first coefficient of 1. 1 times 5 is 5, and we add, we get a positive 2. 2 times 5 is 10, we add, we get a positive 12. 12 times 5 is 60, and we add, and we get 0. So one of our factors is x minus 5. The other factor then would be x squared plus 2x plus 12. And this is still an equation, so I'm still going to write equals 0. Now, what we would do is we would go ahead and we would then factor that polynomial or that quadratic. But we have a problem with this quadratic. If I go and try to look for two numbers that multiply to give me a positive 12 and add to give me a positive 2, no two such numbers exist that are real numbers or that are integers. So this right here is not factorable. And what that tells me is it tells me that it's not going to give us an integer solution. So this is going to be a non-integer solution. And that's important because in order for NPR to work, so we should go back up here to where we learned about NPR, is we should note that both N and R have to be whole numbers. They are representing a number of objects. So we can't have partial objects. We can't have negative objects. N and R have to be whole numbers. So if I have a quadratic that can't factor, it's going to give me a non-integer, or even more important, a non-whole solution, which means that I'm not even going to bother trying to solve that quadratic. I can go ahead and just say I only get one whole number solution. We should be using n, and that is n equals 5. So we should show that we do factor the polynomial. However, we get a factor that will give us a whole solution. We have a quadratic factor that it's not factorable, so that will give us a non-whole solution. Our answer is n is equal to 5. Keep in mind that if this was n permute 2, then we would just have a quadratic equation, and we can just factor the quadratic equation. And then again, you need to double check and make sure that once you find your solutions to the quadratic, that you look for your whole number solutions. That's the end of the first part of permutations. In the second part of permutations, we're going to look at permutations with restrictions and permutations with identical items.